In the previous video, we discussed the first couple of reliability tests, namely thermal cycle, dump heat, humidity freeze, hotspots, and the bypass diode test. In this lecture, we will discuss the remaining reliability tests. Let us first start with the mechanical ones. The purpose of the mechanical load test is to determine whether the modules are able to withstand a certain degree of mechanical stress. The test simulates stresses that can occur by wind, snow, or hail. According to the IEC 61215, this test should be performed after the module was exposed to the dump heat test that we have discussed in the previous video. The dump heat test could have already weakened the module, thus making this mechanical load test more severe. During this test, a certain amount of pressure is applied to the module. The IEC 61215 prescribes a static load of 2,400 Pascal for 1 hour on each side of the module. This corresponds to a wind speed of approximately 130 km per hour. If the module is to be certified for environments where ice and snow can build up, the load is increased to 5,400 Pascal. Although not described by the IEC 61215 standard, the module can also be subjected to a dynamic load. In this case, there is a cyclic pressure applied to the module, usually in the order of 1,000 cycles. Furthermore, there is the hail impact test. The IEC 61215 standard prescribes the use of 11 ice bolts with a diameter of 25 millimeters. The temperature in the test chamber should be -4 degrees centigrade. The ice bolts bombard the modules with a velocity of 80 kilometers per hour. With all mechanical tests, there must be not any major defects after testing. The maximum power at STC and the insulation resistance are checked and used to determine whether the module failed or passed the test. Another mechanical test is the robustness of termination test. This test simulates assembly and various handling actions the module might experience during its lifetime. Various parts of the module, like wires, screws, and connectors, are subjected to tensile and torque stresses. Potential induced degradation occurs at certain modules under the influence of a relatively large voltage potential between the module and the frame. Voltages in PV systems can vary from 500 volts up to 1.5 kilovolts. PID is caused by mobile ions in the module due to the voltage potential. The ions can move away from or into the material depending on the voltage sign. The movement of these ions can damage the module by corrosion and reduce the output power. Not only the magnitude of the voltage potential enhances this effect, but also increased humidity and temperature affects the ion mobility. The correct choice of materials used for the glass, encapsulation, and the other diffusion barriers can reduce or mitigate PID. Another important factor is the type of inverter used in the system. The presence of a transformer in the inverter enables galvanic separation between the DC and AC side of the system. This galvanic separation mitigates the large voltage potential and thereby hampers the PID. Resilience against the PID can be tested in a climate chamber. The minimum criteria for testing are a temperature of 60 degrees centigrade, relative humidity of 85%, and a voltage equal to the rated system voltage. This is usually in the order of 1,000 volts. The minimum testing time is 96 hours. However, many manufacturers test their modules at a higher temperature and for longer times. If the power loss of the module is less than 5% after the test, the module passes the PID test. The UV test is performed to identify materials that degrade when exposed to ultraviolet illumination. In the IEC 61215, it is prescribed to perform this test prior to the thermal cycle and the humidity freeze test. UV can degrade the adhesion and cause delamination between the layers. Furthermore, it can discolor or reduce the elasticity of the encapsulant material. Also, light-induced degradation might play a role when amorphous silicon is incorporated in crystalline silicon technology. Although the IEC 61215 prescribes the UV test, it is criticized that the total exposure is low compared to the exposure of a module experienced outdoors in a 25 years lifetime. In the following video, we will see an example of a PID and a UV test machine as used at EZN. This is an example of a UV testing chamber. The lights are not on since this is harmful for the eyes. The other machine is a climate chamber where potentially induced degradation of modules is tested.
In this chamber we are testing the degradation induced by a high potential in a PV system, especially the large power plants. The voltage can build up to 1000 or even 1500 volt, and here we're testing the durability of the modules with those high voltages compared to the bias volt, which is around 0. In this machine, we're testing the UV resistance of PV modules, but also the individual materials. So here we have special UV lamps to perform the accelerated lifetime tests.
Here we can see how the modules are attached to the PID system. The clamps are attached to the busbar extensions, and by this the high voltage is applied to the module. Besides the durability and the degradation tests, there are also mandatory electrical safety tests. Electrical insulation due to high potential and the wet leakage current are both electrical safety tests. These tests ensure that there is no electric shock hazard when the modules would operate in the field. During the electrical insulation test, a DC voltage of 1000 volts plus 2 times the maximum system voltage is applied for a short amount of time. The module should not break down or experience any other failure by this test. For the wet leakage current test, the module is submerged in a water bath solution. A maximum system voltage is applied between the connectors and the water bath solution for 2 minutes. In both tests, the leakage current is measured. From this, the resistance of the module is derived. In order to pass for both tests, the minimum insulating resistance of the module should be greater than or equal to 40 megaohms per square meter. This brings us to the end lecture series on reliability testing. In this lecture series, we have treated the difference between actual field measurements and the lab testing. Testing modules in the laboratory is the only reasonable way to ensure a minimum quality of the module before it enters the market. The IEC standards provide the minimal quality standards for crystalline silicon modules, thin film modules, and the concentration PV modules. Various tests have been treated which simulate the failure mechanisms that are encountered in the field. According to the IEC standards, these tests have a pass or fail criteria. Nevertheless, lab tests might not simulate all possible failure mechanisms, nor do them provide the tested modules with an expected lifetime.